Okay, so we had left off at page 16 of your notes, so we're going to talk a little bit about gas stoichiometry. So as we had said, at STP, again, this should be 298 Kelvin, not 273. So at STP, 298 Kelvin and 1 atmosphere, 1 mole of gas occupies 22.4 liters of space. So we can use that as a conversion factor when we are doing stoichiometry problem. So in this sample problem here, it says a sample of nitrogen gas has a volume of 1.7 liters of space at STP. How many moles of N2 are present? So the purpose of saying STP is obviously to indicate that we can use this conversion factor. So all you would need to do here is write down 1.75 liters and then multiply by this conversion factor, so liters cancel and you're left with moles. Okay, so pause the screencast for a second and take a moment to do that. So when you do that, you should arrive at an answer of 7.81 times 10 to the negative 2 moles of N2, or 0.0781 moles of N2. Okay, and you could obviously convert that to grams if you needed to. Okay, so here are just some of the ways that we can use this conversion factor and incorporate it into the stoichiometry that we've already talked about. Okay, so take a moment. In this reaction, it reads, what volume of oxygen gas is needed for the complete combustion of 4 liters of propane? So it's a little bit different because you've got information about volume of this particular gas, and you need to use stoichiometry to get over to moles of N2 and then convert from, go to moles of O2 and then convert moles of O2 into liters. So you should use the conversion factor 22.4 liters to 1 mole 2 times in this reaction. Okay, so take a moment to do that. Okay, so when you've done that particular problem, you should get an answer of 20.0 liters of O2. Okay, so scroll on down. Okay, so in the second problem, it says calculate the volume of CO2 at STP produced from the decomposition of 152 grams of calcium carbonate by the following reaction. Okay, so you're starting out with information about a solid and you need to convert into moles of your gas and then convert that into liters. Okay, so pause the screencast and take a moment to do that. Okay, so the answer to this problem up here should be 34.1 liters of CO2. Okay, and then the next problem works the same way. So pause the screencast and take a moment to do that. Okay, so this second problem should have an answer of 3.13 liters of potassium chlorate. Okay, it's okay if you're slightly off. Okay. Okay, and now in this particular reaction it reads, in this particular problem it reads, when 3 liters of propane gas is completely combusted to form water vapor and carbon dioxide at STP, what mass of water vapor will result? Okay, so in this case, you're given a volume of your gas to begin with, and so then you can easily convert that into moles of gas given the 22.4 liters per mole conversion factor. Once you figure out moles of your gas, then you can convert into moles of O2 and then grams of O2 just using regular stoichiometry. So take a moment to pause the screencast and work that problem. Okay, so the answer there should be 9.64 grams of H2O. Okay, so scroll on down. Okay, so in this case, it says if 5 liters of nitrogen reacts completely at STP, how many grams of ammonia are produced? Okay, so you should be able to convert from your volume of gas into moles of gas, and again, just convert into grams of your NH3 gas or your ammonia gas. Okay, so take a moment to do that. Pause the screencast. So the answer there should be 7.60 grams of ammonia. Okay. All right, so this, what I want you to do is just draw an X through this whole page, page 18. This doesn't actually deal with non-STP conditions. At the end of this set of notes, we'll get into looking at some problems that involve what we call real gases, which is basically a non-ideal gas. So remember we talked about the ideal gas law and how ideal gases follow kinetic molecular theory, and that's why we can use these equations to interpret the behaviors of gases. But the reality is that no gas exactly follows ideal gas behavior. So real gases best approach ideal gas behavior under conditions of high pressure and low temperature. Okay, so you need to know that. Real gases best approach ideal gas behavior under conditions of high temperature and low pressure. And that's because molecules move faster and more freely and have more energy to break any potential intermolecular forces between gas particles under these conditions. Okay, so the higher your temperature, the lower the pressure, the better the ideal gas law is at predicting the properties of gases. Okay, so let's move on to page 19 and we'll talk about Dalton's law of partial pressures. Okay, so this is really a simple idea here. So the idea is that in order to figure out the total pressure of a combination of gases, you just need to add together the partial pressures of each gas individually. Okay, so that equation is just represented here by P total or pressure total equals the pressure of one individual gas plus the pressure of another plus the pressure of another. Okay, and obviously when you add those, they should all bear the same units, and we'll continue to use atmospheres for that. Okay, so this problem reads, calculate the total pressure of a mixture of oxygen and helium. The partial pressure of oxygen is 9.3 and the partial pressure of helium is 2.4 atmospheres. Okay, so take a moment to figure out the total pressure there. Okay, and so when you do that, you obviously just add them together and your total pressure should be 11.7 atmospheres. Okay, so let's scroll down to this next problem. So this works no differently. You just have 3 gases and you're still finding the total pressure. So pause the screencast and take a moment to figure out the total pressure there. Okay, so when you do that, you should find that the total pressure, oh, I'm sorry, I just realized that you're finding a partial pressure and you're given the total pressure. So obviously you use the same formula, and so your pressure, partial pressure of O2 should be 0.15 atmospheres. Okay, so go ahead and look at this last problem. So again, you're given the total pressure, it's in millimeters of mercury, and you're just finding the partial pressure of an individual gas. Okay, and you can go ahead and solve in millimeters mercury. Okay, so take a moment, pause the screencast, and work that problem. Okay, so your answer there should be the partial pressure of hydrogen gas is 161 millimeters of mercury. Okay. All right, so what we're going to do, obviously this concept is very simple. What we can start to do is think about how we can incorporate Dalton's law of partial pressures into PV equals nRT. Okay, so all of this is just a derivation for the idea that the total pressure, okay, is equal to the total number of moles of a particular gas times RT over V. So in other words, if we're thinking about a partial pressure, we can incorporate the partial number of moles in order to calculate the partial pressure of an individual gas. Okay, and we can obviously do that for multiple individual gases. Okay, and then in order to find the total pressure, we can add together those calculated partial pressures that we found by doing individual PV equals nRT problems. Okay, so another way to think of this is that our partial pressure divided by our total pressure is equal to or proportional to our partial number of moles of gas divided by the total number of moles of gas. Okay, so when you look at this problem here, it reads a mixture of gases contains 1.5 moles of oxygen, 7.5 moles of nitrogen, and 0.5 moles of carbon dioxide. If the total pressure exerted by the mixture is 800 millimeters of mercury, what are the partial pressures of each gas in the mixture? Okay, so what you're going to want to do here is incorporate this equation up here, okay, and you can leave out the chi that's in the center, okay, and you're going to want to isolate the P1, okay, because you know that that's what you're solving for, because you know the partial moles of gas for each gas. You can add them all together to figure out N total, and then you know what the total pressure is. Okay, so you want to solve for P1 for each of the gases individually. Okay, so take a moment to do that. And pause the screencast. Okay, so for instance, for the partial pressure of oxygen, you should be multiplying the total pressure, which is 800 millimeters of mercury, by the number of moles of oxygen, which is 1.5, and then dividing by the total number of moles, which is 9.5 moles. So your partial pressure of oxygen should be 126 millimeters of mercury. Okay, it's fine if you found it in atmospheres, but there's no need to convert here, just because it's a proportion in this way. Okay, and then your partial pressure for nitrogen gas should be 632 millimeters of mercury, and then your partial pressure for carbon dioxide should be 42 millimeters of mercury. Okay, so this next problem has multiple parts. So it reads a mixture of 1 gram of hydrogen gas and 1 gram of helium gas is placed in a 1-liter container at 27 degrees Celsius. Calculate the mole fraction and the partial pressure of each gas. Then calculate the total pressure in the container. Okay, so there are multiple parts here that we need to be concerned with. So the first thing I want you to do is figure out what the mole fraction is. So that can be done, remember that's just the partial number of moles divided by the total number of moles for each element. Okay, so you should have a mole fraction for hydrogen and a mole fraction for helium. Okay, so you can obviously find the number of moles of each gas by converting from grams to moles, and then you can do your division there. Okay, so pause the screencast for a second and take a moment to find the mole fractions for each gas. Okay, so when you do that, you should find that the mole fraction for hydrogen is 0.667, and the mole fraction for helium is 0.333, okay? And you don't need any units on that because you have moles divided by moles, and so they cancel out, okay? Okay, so I'm going to stop for a second because the time for this screencast is about to run out, so I'll transition the next part of this problem onto another screencast and we'll pick up there.